Hey there, algebra kids. Welcome to video 4.6, your introduction to graphing quadratic functions. You're going to see quite a few examples today, but just make sure you keep your eyes peeled for what we did today in class, because I'm going to teach you how to use that information to be able to do the skill that you need for tomorrow in class. So just be prepared for that. So first, some definitions. What a quadratic function is, it's a second-degree polynomial that creates a U-shaped graph called a parabola. So it can create a graph that looks like this or like this on your coordinate plane. And you know you have a quadratic when you see this degree of 2, and that's the highest degree. If y equals x squared plus 3x plus 2, that's an example. You can get that down. Some other examples that you would see in real life are parabolas like the St. Louis Arch, the McDonald's Golden Arches. This cool roller coaster here makes a parabola, and also the popular game of Angry Birds. Every time you shoot a bird off to hit one of those little piggies, or in this case monkeys, you always make a parabola with the path of the bird. So here are some other definitions. There's the quadratic function definition that you got down before. We also have maximum and minimum. So for maximum, it's the highest point of the parabola, and for minimum, it would be the lowest point of the parabola. So max and min, highest and lowest. The vertex is the maximum or minimum of the parabola. It's also the turning point. So wherever, if you see that U, upside down U, or a regular U, that turning point, that is the vertex. And then the zeros. The zeros are the points where the parabola crosses the x-axis. So if we have this parabola here, this point here, and this point here would be the x-intercepts, or the zeros of the parabola. So make sure you get those definitions down. So we're going to start off learning this skill by just using a standard quadratic function. And we know this is a quadratic because it has the lowest exponent of 2. It is a second-degree polynomial. Also, I need you to draw this coordinate plane and this xy table and be ready to fill it out. So we're going to start solving this by just plugging in our x values into the function and evaluating for y. So let's start with -4. So y equals, in parentheses, -4 squared plus 2 times -4 plus 1. Y equals -4 squared is 16 plus 2 times -4 is -8 plus 1. 16 plus -8 is 8. 8 plus 1. So y equals 9 when x equals -4. So I went ahead and filled out the rest of the table for you, but I got all of these values by plugging the x value into the function. And what I need to do next is plot these points and graph my parabola. So I'm going to plot each coordinate of xy. So my first one is -4, 9. I go from -4 to +9, and it is off the grid, but that is okay, so it'll be somewhere up here. And I have -3. I'm sorry, that should be right there. I have -3 and a +4, which is right here. And I have -2 and a +1, just right here, and -1, 0. Back to 0, +1, +1, +4, and 2, +9, which is going to end me up back right there. And then I'm just going to connect all those points, and I get this U shape. I'm sorry, that is not the most accurate graph, but that is how you can easily graph a quadratic function without knowing any other information. You just make your xy table and plug your values in. You can also graph on your calculator. So what I did is I went to y equals button, and I entered x squared plus 2x plus 1. I got my x from this button right here, and my x squared button is right down here. It says x squared on it. And then to see it, I can hit the graph function, and that definitely matches what we had in our last slide. And then also, I can easily see my table by just hitting second function table, and it gives me my table values that match what we had in our last one. So here we have our application problem where we're maximizing area, and this should look familiar to what you did today when you were trying to find maximum areas given certain lengths. So problem 1 from extended practice 4.5, you wanted to maximize the area of a rectangle with a perimeter of 12 meters. So we have our table of lengths and areas here, and we know that when our length is 1, we definitely have to have widths of 5 because we want to make it equal our perimeter of 12 meters, and 1 plus 5 plus 1 plus 5 is 12. And then 1 times 5, which length times width gives us area, is 5. So 5 meters squared is our area. But I got a lot of questions yesterday on how do I graph this. You guys saw this chart or graph that you had to fill out, but you didn't quite know how to graph it, and that's perfectly fine because I'm going to show you right now. We have our x-axis labeled length and our area labeled, our y-axis labeled with area. So we're just going to treat length and area as an xy coordinate and plot them on our graph. So I made the scale on each axis. I have length 1 through 5 because that is how high it goes with our length, and then area I went up to 10 because our highest area was 9. I'm just going to plot these points. So I have a plot of length of 1 and area of 5 is right here, length of 2 and area of 8 is right there, length of 3, area of 9, length of 4, area of 8, and length of 5, area of 5. And as we can see, that makes a beautiful parabola. And this makes sense because what we were talking about yesterday, or I mean today, is you saw a pattern between your areas that it goes up, it reaches a high point, and then it goes back down in the same pattern. So even if we didn't have this table here and we were asked, well, what's the maximum area? You can read your graph by looking at the vertex. The vertex will always show you your maximum area when you're comparing the length to area. So with a length of 3, we have our maximum area of 9. So you can just read your graph to see your maximum areas, and you don't have to worry about your table if you don't have one. Conversely, we can also see where we have lower areas, and we can see our lowest area is between 0 and 1. We have a length of 0 and 1, and also when we have a length greater than 5. So just know that this is how we can read our parabolas when it relates to area. Highest point shows greatest area, and lowest points show the smallest area. So your hot question of the day. I just explained it in the last slide, so if you need to go back, go ahead and do that. Please describe what the highest point, the vertex of a parabola, shows us that compares the length of a rectangle to its area. So what do you know about the highest point of a parabola that when you're comparing the length to the area? Go ahead and answer that on your hot question link, and good luck.